So, well, the total mole on this side is how much? 3 moles. Okay, and on that side it is 2 moles. Right, and they are all gases. That plays the part as well. Right, now, if we make the container smaller, which side will be favored? The true side, the right side. Why? Because it's less moles, less particles. And if we make the container bigger, it's going to change itself so that it fills more space. So it's going to favor the left side. Okay, and that's the effect of pressure. Why am I here now? Anyway, all right, so let's see there the effects of pressure. If we increase the pressure, and that's the same as if you lower or decrease the volume. Increase pressure means decrease the volume. Then the reaction with the lowest amount of moles will be favored. Takes up a smaller space. Okay, and if we decrease the pressure, meaning we increase the volume, make it bigger, then the reaction with the highest amount of moles will be favored. And then again, the Kc value will not, the change in pressure will not change the Kc value, because the changing of the pressure for a gas, it is like changing the concentration. Okay, it has the same idea, vibe going on. Okay, so I'm going to read. It says there, pressure only affects equilibrium in a system that includes gases. So only where we have gases. Okay, not aqueous solutions, not solids. Only where we have gases. If the pressure is increased, then the reaction is driven in the direction that relieves the pressure. Okay, and then what I said here is a change in pressure actually causes, that's what I said there, the change in pressure actually causes a change in concentration, and as already confirmed, that does not change the Kc value. Okay, so let's look at the first reaction here. What is this reaction's name again? The Haber process. Wait. I need to have sweets again. Next term. It's too late now. We have 1 day left, and if I buy sweets now, I'll eat it. The whole exam. And I'm trying to shed the baby weight. Alright. Okay, so there we see we have the Haber process. And you can see it's 1 mole plus 3 moles, so that gives you 4 moles versus 2 moles. Okay, so, and as you can see on the right-hand side, I showed you a diagram. So here you have 1, 2, 3, 4 molecules versus 2 molecules. And even though these molecules are bigger, remember molecules actually, it's bigger, but it's still like teeny tiny small. Okay, so it looks bigger like when you draw it like this, but it's still very small. And gases actually take up space due to their movement. The more they move, the more they collide. Okay, that's what actually gives it space. All right, so it says that if the pressure on the system is increased, pressure increased, meaning the volume decreases, like here. Then the reaction will compensate by producing more ammonia to decrease the volume of the gases, because there's 2 moles instead of 4 moles. And thus the pressure will be decreased. Okay. Then, if we look at this reaction here, where we have 2 mole of nitrogen dioxide versus 1 mole of dinitrogen tetroxide. Okay, so mole ratio there is 2 to 1. Then it says there a decrease in volume. So decrease in volume, meaning we go to the side with a smaller mole. No. Yes, the decrease in volume increases the pressure. Yeah. Decrease in volume increases the pressure. So it goes to the side with the smallest mole. So what will we see in the container? We will see it becomes colorless. Okay, so it increases the amount of dinitrogen tetroxide. And then an extra thing that we can do. So instead of changing the volume of the container, you can keep the size of the container the same, but what you can do is you can introduce an inert gas. What is an inert gas? A gas that do not react. Okay, something that does not react. It's just there, it just takes up space. Okay, so the inert gases here that they speak of is the noble gases. Okay, because we know the noble gases, they do not like to react with anything else. They're perfect. Okay, so if you add a gas like that, so you have this at equilibrium, now you pump it in with more gas particles, but they do not react. What are you basically doing? You're increasing the pressure. You are making the volume that the gases that wants to react can move in. You're changing that, making it smaller, limiting them. So if you introduce an inert gas, you add that to it, then you are increasing the pressure. Okay? And then increasing the pressure goes to the side with the smallest mole, so it will produce more of that. Sharp? Okay. And then the effect of a catalyst. The catalyst only affects the rate of a reaction. It only causes it to go faster or slower. So a catalyst increases the rate of both the forward and the reverse reaction. So equilibrium is reached faster, but it has no effect on equilibrium. Meaning it doesn't shift it to the right or to the left. Okay, so thus it will have no effect on the Kc value as well. Okay, then a last thing that they can ask, they don't ask that often, but that they can ask, is if you look at salts, when salts dissolve in water, and there I give you any salt, I give you potassium chloride. When that is dissolved in water to a saturation point, what is a saturation point? Where it doesn't want to dissolve anymore. It's like when you add sugar to your coffee, at a certain point when you get to how many spoons? 4? 5 spoons. Then the sugar doesn't want to dissolve anymore. Right? So that is the saturation point. When it reaches the how many do you add in your coffee, Liakwe? 6. I drink no sugar. Guys, you are going to get diabetes. Still, how many teas or coffees do you drink a day? Yeah. 1 is enough. Then you can drink your...
6.
Yeah. Okay. Anyway, right. Thank you. Okay. Thank you, guys. Shh. All right. So when you dissolve a salt in water, it reaches a saturation point. That's where it doesn't want to dissolve anymore. So when you add more sugar, salt, whatever, then if it wants to dissolve, a particle needs to form a solid crystal again. And then it dissolves, solid crystal, dissolve, solid crystal. So when you reach saturation point, it results in a dynamic equilibrium. Okay? And there you can see it can be represented there, where you have potassium chloride, the salt, and then the forward and reverse reaction, you get the potassium ion aqueous. What does aqueous mean again? Dissolved in water, surrounded by water, and your chloride ion. When saturated, the rate of the forward reaction, where it dissolves soluble, is equal to the rate of the reverse reaction when it forms crystals again. Okay, so if this dissolves, then it forms crystal. Dissolve, form crystals. Okay, right. Now here we see a table for the solubility of a salt in water versus temperature. Okay, now what conclusion can we draw from temperature versus solubility? For most of them, for everyone except cesium sulfate. The higher the better it dissolves. Okay, now I want to know why. Why? Why does it dissolve better when the temperature goes higher? Yes. Okay, that is the rate at which it dissolves. Okay, so if this was the rate at which it dissolves, then yes, your answer is correct. But that's not, it says it dissolves better, the solubility. So the warmer it gets, the better it dissolves. Meaning the more reactants you get. Not the faster you get there, the more you get.
Yes, ma'am.
I'm asking why. Okay. Yes. No, that's what she said. Think about we are looking not at rate, we are looking at three things: concentration, temperature, pressure. What are we changing here? Temperature. Okay. So I just want to follow my correct order here. Okay, so what we see here is when the temperature increases, the salt dissolves better.
Is it good like they're reaching their boiling point? So
No. Boiling point of a salt is like in the thousands. This is dissolving it in water. Yes.
It's a difference when a substance dissolves and when it boils.
Dissolves is when you add it in water,
So does it
and boils is there's no water, you put a flame underneath. Okay. So when it dissolves better, it means the forward reaction is favored. Right? Okay. So that means thus the forward reaction is favored. With whose theory are we busy with? Le Chatelier's principle. Le Chatelier's principle says that if we increase the temperature, what does the reaction want to do? Decrease the temperature. By doing what? Favors the endothermic reaction. So it means when it was heated, the endothermic reaction was favored. Yes? Okay? So we say, according to, now I'm going to abbreviate, Le Chatelier. An increase in temperature will favor the endothermic reaction. Okay, so what did we just say? We said the forward is favored, and we said the endo is favored. So what is the forward reaction here? Endothermic. Thus, the forward reaction is endothermic. Okay, wait, I just want to complete my thought. So, when I ask you why does it dissolve better when the temperature is increased, it's because the dissolving of salts is endothermic. The more you heat it up, the better it will dissolve. Okay, so what you can do is this afternoon, take water, and then you dissolve, and you take the temperature, and then you dissolve salt in it, and you take the temperature again, and it should feel a bit colder. Okay, so when you dissolve salt in water, it actually cools down the water a little bit. Yes?
Why don't we know in the principle did the carbon to be leaving?
Don't worry, you'll lose 1 mark. It's at the end.
So
Alright, yes.
was it right if like if one
Yes, the one was yeah. Alright, so it says there at the bottom, as shown in the curve, the solubility is endothermic. To dissolve something, a salt in water, it's endothermic. So when you raise the temperature, it dissolves more. And obviously when you drop the temperature, when it makes colder, it dissolves less. Okay, all of the salts are like that, as you can see. Okay, all of the salts are like that, except for this one. This one actually is when you make it warmer, it dissolves less. Okay, so from the graph we can see that. Okay, then the effect of a common ion, the common ion effect. Okay, if we look at this reaction here, you can see it's normal table salt that we add to water and it dissolves. All right, and go, and it reaches equilibrium. Okay, now what we can do is, if we want to go back, if we want to produce more salt, then we can add an ion that is common, that is the same here. So I do not have to add sodium and chloride. What I can do is I can say, all right, I get the chloride ion in hydrochloric acid, aqueous. Right? What is that basically? It is basically a hydrogen ion and a chlorine ion that I have, the aqueous solution. So if I have table salt that is dissolved and I add hydrochloric acid to it, what I'm basically doing is I'm adding a chloride ion. Where's the chloride ion? There's it. So I'm adding that. What will the reaction do? Shifts to the left, so then you'll see salt crystals form. Okay, so it says there at the bottom, when concentrated hydrochloric acid is added, a white precipitate. Precipitate is a solid. Okay, like normally a powder, crystally type of thing. A white precipitate, a solid, which is salt, will form. Why does that happen? Because concentrated hydrochloric acid has the chloride ion in it, and that is the common ion. So that chloride ion is the common ion. So ion that's the same for both. So when we add the chloride ion, the equilibrium will shift to the left, making more sodium chloride. So the equilibrium shifts to the left, forming the white precipitate. Alright, then the effects of strong and weak acids. This is actually your next chapter, but I just want to speak about it quickly. If we look at hydrochloric acid, now hydrochloric acid, when it is produced, it's very warm, it is actually a gas. Then they let that gas dissolve in water, a pure liquid. Okay, now, hydrochloric acid is a strong acid. It's a very, very strong acid. And that ionizes, reacts with water, almost entirely. Meaning, almost, if you have 100 molecules, of sodium hydrochloric acid, then 98% of them will dissolve with water, will react with water, and only 2 molecules won't. Okay, so ionizes almost completely means almost all of your molecules will react with water. And we show that by saying the equilibrium lies to the right. So we have a long arrow to the right and then a short arrow back. Equilibrium lies to the right, and that what's happening here is that hydrogen will act with water to get the, what do you call this molecule again? Hydronium ion. Well done. If I had a sweet, I would have given it. I owe you nothing. Yo. All right. The hydronium ion. But for a sweet, I'll write it down there on the board. What type of bond do you find in the hydronium ion? No. But what type of covalent bond? No. A certain type of covalent bond. No. That is an intermolecular force. A dative covalent bond. Does that ring a bell? Okay, so in here you find a dative covalent bond. All right. Then, if you look at acetic acid, anyone give me the formula for acetic acid? The organic chemistry name for it is ethanoic acid. Yeah, it means 2. You have CH3COOH. Remember that one? Acetic acid. Now, when that is produced, it is a liquid, and they will dissolve that in water. Now, acetic acid is considered a weak acid. So that means it will ionize only slightly in water. Okay, now if it ionizes only slightly, it means if you have 100 molecules of that, then let's say only 10 of them will actually ionize and the other 90 will stay as it is. Okay, so then we say there's a short arrow to the left and to the front and a long arrow back. Okay, now it is this hydrogen that will react with water or bond with water to get the hydronium ion and the acetate ion. Oopsie. Acetate ion. Stayed past. I saw in your body language. You thought this period couldn't be any longer. All right. So the next page is a chapter that is taken out of your syllabus. Okay? But it is something that they do still ask in your question papers, but you don't need to know a lot of facts. Okay, so what you do need to know, be aware of, is the name, the Haber process. Spoke about that. And there you see the reaction. So you don't need to know the reaction off by heart. They'll almost probably give it to you. Okay, but just be aware that goes with that. And then you can see it's an exothermic reaction. An exothermic reaction. Okay, now things that the learners had to know a few years ago, they had to know what was the catalyst that was used, what is the temperatures, what is the pressures, and. You don't need to know that. The only thing that I want you to see is if this is an exothermic reaction, how will they produce more ammonia if it is exothermic? Will they heat the reaction up or cool it down? Cool it down, because then it wants to heat it up again. Now, they actually do that, and they cool it down to 500 degrees Celsius. Okay, so this reaction is actually at 1000, 1200 degrees Celsius, and then they cool it down to 500. So cooling it down is a relative term. Okay, the next one there is the contact process. The contact process, and that is to make, at the end of the day, the contact process has 5 steps, I think. It is to produce sulfuric acid. Okay, so think you can't make contact with sulfuric acid. It will burn your skin. Okay, now this is the one step in this contact process that you have to know, but we've worked with it. I showed it to you. It was one of my examples today. Again, you can see it's an exothermic reaction. Okay, and again, to favor the forward reaction, you must cool it down, and they cool it to 450 degrees Celsius. Okay, so again, a relative concept. And then the last reaction there is the Ostwald process. Ostwald process. And that is to produce nitric acid. Okay, now there in the Ostwald process, there's a few steps. The one that they ask in your question papers the most is the second step there. Okay, and then you can see again it is an exothermic reaction, and they cool it down to 900 degrees Celsius. Okay, right, so again, you don't need to know all of these facts off by heart. I just want you to have seen these equations. It's going to be in our homework examples that we're going to do together now. Okay, and so just be aware of it. It's all exothermic reactions, and they use it, all of these things, they use it to make, in the industry, in the fertilizer industry. So you actually had a whole chapter on fertilizers that they've taken out due to COVID. Okay, right. So your homework was 2, 3, 4, and then we're going to go on 5, 6, 7, 8, 9, 10, all of them. And then for tomorrow, I want you, so we're going to start with this work. If we finish, the rest will be homework. Okay, what we do not finish. And then for tomorrow, I want you to please bring that other booklet. I'm still copying the booklet for you to go on. I want you to bring this one, please. You have one? I thought you said you didn't have one. Okay. All right. Okay, sorry. So tomorrow, please bring this booklet with. Declan, this one. Okay, so let's go. Open your writing book, please, and we're going to start by marking the homework. Or did I gave the answers there at the back, no? Did I not? Okay, I see I don't have that chapter. Okay. Did anyone struggle with question 2? Question, so you can mark yourself, right? Question 3?
No.
Question 4?
Yes.
Okay, let's do question 4. Okay, they say there, calculate the value of the Kc for the reaction if at equilibrium we have so much hydrogen, so much iodine, and so much hydrogen iodide, and they give you the balanced equation. Was it balanced? Yes, it was balanced. Alright, you can see there that they are all in the gas phase, so we are happy with that, we're fine. And they say at equilibrium. They say at equilibrium, we have the following, and I know it's in grams, I just want to write it down. We have 6 grams of that, and 508 grams of that, and 384 grams of that. Okay, now to calculate the Kc expression, what will our formula be, Chabu? of? What's the product's name? A name. Hydrogen iodide over hydrogen gas and iodine gas. Thank you very much. Okay, now what does this square brackets mean, Princess? No, the square brackets, what does it mean? Concentration of. So we must change these grams to concentration. Okay, now there's two formulas for concentration. The one is this, and the other one is this. Okay, now since they give us grams, I'm going to change this mass into concentration with this formula. Okay, so then I will have for this one, I will have 6 over, what's the molar mass of hydrogen, Mosi? 2, well it's 1, but there's 2 hydrogens, so it's 2. And the volume they give us there as 2 cubic decimeters. Okay, this one will be 508. Liaku, what is the molar mass of iodine? I just want to check something if I did this with you. Can I check your file, please? Okay. No. So, at the beginning of the year somewhere, I gave you hello, I will do what right with you. At the beginning of the year, I gave you, we did take it apart and we put it in okay? The data sheets. Yes? It was in your exam guidelines. So go to your periodic table that's taken on. Yes, Leaku, what is it? Okay, but what is iodine? It is a diatomic molecule. Okay, so you must take that, you said 127 and times it by 2. And then the volume is also 2. The volume is the same for all of them. Okay, and then this one is 384. The molar mass for that will be 128. How did I get to 128? It's 127 of iodine plus hydrogen, 1. So 128. And the volume is 2. Okay, so what I want you to quickly do together is write your answers for all of them and substitute them into your equation. Yes, Bongi? Because that's the formula says times the volume. And the volume they give you in the notes is 2. Morning. Well, I know what it was. I think this is what he wants, but my
He's been here for too long now.
all right. Boki, what did you get for the first one? 1.5. What did you get for the second one, Tawana? Exactly 1. That's true. And the last one, Antoinette? I get 1.5. 1.5. All right. Then we substitute that in our equation. So that's 1.5 squared over 1.5 times 1. And without a calculator, Declan, what is that?
Will be one.
What?
No, it's will be
What is x squared over x times 1?
X.
X. So the answer is 1.5. Now I see you make a mistake there. Please, when you substitute your values, lose the square brackets. So no square brackets. Do you see that?
Yeah.
Yes? What's wrong?
So I can't
The moles, yes? And then you see how they reacted with one another. Okay, now, why are you wrong? If you read the question there, they say calculate the Kc value for the reaction if at equilibrium. So what you thought in your head is that is what you had at the beginning. Okay, so but that is not what they said. They said at the end, after it has reacted with one another, this is what is left over. Okay, so let's quickly look at the questions. At question 2, they said at equilibrium, you have that. At question 3, they say at equilibrium, you have that. Question 4, at equilibrium. Okay, the different thing here is, okay, look at question 8 quickly. Quickly go to question 8 on the next page. There they say you have this reaction. Then they say you get an equilibrium at a container at that temperature. 50 grams of so much is initially added in the container, and at equilibrium it is measured that you have so much left. Then you do the mole table. So if they give you things at the beginning and things at the end, then mole table. If they only say at equilibrium, then you don't have to do mole table. Okay? Yes. Of 1.5. Let me see. I think it might have been by accident due to the mole ratio. Yeah, due to the mole ratio in this instance, you luckily got to the answer. But no, see, you do something with. How can you say no? You say there minus 1, minus 2, plus 3. But the mole ratio is 1 to 2. It should be minus 1, minus 1, plus 2. So luckily. Okay. Right. Then let's do our notes off. I'm just going to give it a moment. Let's go together to question 5. Okay. At question 5, they say there. Now I want you to rewrite that equation, please. For question 5, just rewrite the equation. That is the equation that you find in the Ostwald, not the Ostwald, the contact process, where sulfur dioxide gas reacts with oxygen to give you sulfur trioxide. Now, the reason why I want you guys to rewrite the formula always is to check the phase subscripts. Okay? You can see gas, 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 so you are happy. You don't have to make like a big star anywhere to remind you of anything. Okay, now what I want to do as well is they didn't give us the heat of the reaction, but we know that this is an exothermic reaction. An exothermic reaction. Okay, so you can write that down. And then I want you to write down the mole ratio. So here we have 3 moles and here we have 2 moles. Okay, sorry, that means that the forward reaction is exothermic. Okay, let's look at question 5a. They ask, what effect will there be on the equilibrium position if we increase the concentration of sulfur dioxide. Okay, so we're at equilibrium, and now we're adding the concentration of sulfur dioxide. It will shift to the right. So we're going to say that means equilibrium shifts to the right. What will happen to the Kc value? No effect. It will not change. What is the only thing that can change the Kc value? Temperature. Okay. B. They say we decrease the concentration of sulfur trioxide. Okay, so we're here again. We decrease the concentration of sulfur trioxide. What will happen? It will shift to the right again. What will happen to the Kc? No effect. Right. Then they ask increasing the pressure on the system. Increasing the pressure on the system. So increasing the pressure. That means we're doing what with the volume, Declan? We're decreasing the volume. Okay, so that means it's going to go to the right or the left? To the right. Smaller moles. Okay, now what I want you to please do for homework. Okay, finish number 5. There's one question left for number 5, number 5D. Then I want you to also, you can skip question 6. Please do question 7. Okay, I'm not going to give you everything. Okay, I want you to do 7, 9 and 10. 7, 9 and 10, please. 7, there's also a mole table in, yes. No, wait. Yeah.